All right, welcome to the lesson today on combined vapor pressure and boiling point in part one, in which we're going to look at how molecules evaporate and how that the mechanism by which they evaporate leads to boiling. And then we're going to look at something called phase diagrams, in which we're going to look at how all the various phases of matter coexist within different regions of pressure and temperature. So to start off, let's go back to evaporation. Evaporation is a pretty interesting phenomenon, and there's a lot going on there. We can have evaporation of the liquid where the liquid is changing to a vapor at the surface. So if we look at the surface of this is like we saw in the previous lesson, where the molecule, where's my pen? Molecules are evaporating. As we see down here, the molecules are evaporating at the surface. Now, if they have enough kinetic energy, so if we have a molecule, I better find another color to get in there. So if we have a molecule that's inside here and has enough kinetic energy, it will be able to escape and form a gas. There's a concept called volatility, which you've probably encountered before, but may not have known what it is. Volatility is the ease with which a liquid evaporates. All right, so it sounds like a simple concept, but it entails a few things. To be volatile is to be said to be easy to evaporate, so it's a material that evaporates easily. And you may have seen this if you've ever spilled a liquid like gasoline on the sidewalk. It evaporates pretty quickly. Gasoline is said to be volatile. Water is somewhat less volatile. It doesn't evaporate that quickly. And there are liquids that are even harder to evaporate. And the differences between them are in terms of the intermolecular force. Liquids like water that have higher intermolecular forces have lower volatility. And so they evaporate more slowly. So we've got this idea now that there's a speed, a rate with which materials can evaporate, and this rate will tie into the intermolecular forces in a few minutes. Okay, let me get rid of the underlining, the proofing, spell checking. So what can happen is if we have an open system like on the left, when there's no lid, in this open system, molecules can escape, and we're never going to build up what we call a vapor pressure. We're never going to build up the sample inside the container, because the sample, as it's shown here, everything can evaporate, and eventually all of the liquid in here, whether it's water or whatever else it is, will evaporate. This says water here, but it could be any liquid. If instead we put a cap on it, we put a lid on this now nothing can escape. So we do have molecules coming out into the gas phase like before, and there's a rate with which that happens. So the particles evaporate and pressure starts to build up, and they evaporate at a certain rate. So we have a rate of evaporation. As that pressure builds up, now we're going to start having some of these particles recondensing, and there's a rate of condensation. And what happens is, as that rate of condensation increases, so the rate of evaporation depends on the temperature, and it depends on the liquid. We'll see how that is below. The rate of condensation depends only on the pressure. So as that pressure builds up, there becomes some pressure at which the rate of evaporation becomes equal to the rate of condensation. And this equilibrium, in which the two rates of the two opposite things happen and becomes equal, is the pressure at which this happens is called the vapor pressure, or sometimes it's called the equilibrium vapor pressure. And this is the vapor pressure that we had to subtract off in the eudiometer lab because we did our experiment over water. And so anytime you had the water in a closed system, you built up a particular pressure. This equilibrium can be represented by an equation. In this case, the equation is that the water as a liquid, and I'm going to throw a funky arrow at you now. This is an arrow that has, it's actually two arrows, one pointing to the right, and we're going to use a half-headed arrow to make it compact, and another arrow pointing to the left. And we're making H2O gas here. And what this is showing here is the evaporation and the condensation. So evaporation to the right and condensation coming to the left. And this is our first look at what we call a reversible process. And we'll see more of these over the next few weeks and couple of months. So we've got this vapor pressure that builds up. And this vapor pressure is indicative of a few things about this system. So the vapor pressure does depend on the temperature. And at the right, I've got 5 curves. There's an E in there as well down below, in which we look at the vapor pressure. So this is the vapor pressure on the y-axis as a function of temperature on the x-axis. And that should not be quite as close there. Let me see if I can move that down a little bit. It's not letting me grab. Oh, that's why, because I've got my pen on. So let's see if I can grab that and pull it down a little bit. There we go. Give us a little room. Okay, so this vapor pressure of a particular liquid, you can see as a function of temperature, the vapor pressure is increasing. So if we look at the temperature, for any liquid, liquid A is something called carbon disulfide. Then we have methanol, ethanol. We had that in our reactions lab. We have water, and we have something called aniline. What's important is going to be not the specific liquid, but its intermolecular forces. So at a higher temperature for each the same liquid, so you follow one of these curves up, you have a higher kinetic energy, higher average kinetic energy. So let's pick D, since that's water. And so as you move up the curve, higher kinetic energy gives you a faster rate of evaporation, so faster evaporation and a higher vapor pressure. Okay, so more particles have enough energy to evaporate, and so as the temperature goes up, the rate goes up, and the vapor pressure, VAP, also goes up. All right, so that you can see for any particular system there, an increase in the temperature giving you an increase in the vapor pressure. And don't worry about the function. You'll just have these curves to work with. Now, the second dependence has to do with, as we said before, volatility depends on the intermolecular forces. And if you have higher intermolecular forces, that's a lower volatility. That means a lower rate of evaporation, and that means a lower vapor pressure at a given temperature if we compare two or more liquids at the same temperature. So I'm going to draw a line here, starting with A, and let's say, sorry about that. Let's say at 40 degrees C, we have a vapor pressure of A just above 600 millimeters of mercury. That's because A has weak intermolecular forces. So high vapor pressure means weaker IMFs. Now, at the same temperature as we come down, we go through B, C, D, and eventually we get to E. And as we come down here, we get to low vapor pressure. The lower the vapor pressure gives us stronger intermolecular forces. So we can compare different liquids at the same temperature, and we can get a sense of their intermolecular forces, and we can get a sense, if we know what their intermolecular forces are, we can get a sense for their vapor pressure. So as the intermolecular forces go up, the vapor pressure, the rate first, the rate of evaporation goes down because it's less volatile, and that means the vapor pressure also goes down. And this set of curves will play significantly in your homework tonight. All right, so we've got this look at different liquids at different vapor at the same temperature, and we have a function here to show you how the vapor pressure, change in vapor pressure shows us the change in intermolecular forces. Okay, so molecules, liquids can evaporate. Now, the ultimate in evaporation is when we get to boiling. Boiling is a very specific way of evaporation. When we talk about evaporation, the evaporation we're talking about is evaporation at the surface. But boiling now is evaporation not at the surface, but inside the liquid. It makes sense that there are going to be molecules that are trapped in the liquid that have enough energy to evaporate. And if they get together with enough other molecules that have enough energy to evaporate, they can actually form bubbles. But this formation of the bubbles is difficult, is problematic. This formation of the bubbles doesn't happen if the pressure is too high, or I should say if the vapor pressure is too low. So these bubbles that you see over here, these bubbles can form, and you've seen bubbles forming in boiling water. These aren't the bubbles that form initially. The bubbles that form initially, we'll talk about those when we talk about solutions where gases that are dissolved will come out of the solution. And that's what you see first. But these are the bubbles of the rolling boil. Bubbles can form only when the vapor pressure can overcome the pressure of the atmosphere on the surface. So we have to be able to overcome. So we've got this pressure of the atmosphere pushing down on the surface. And the bubbles need to be able to push out against that vapor pressure and to be able to survive. And when they do, then the bubbles rise to the surface because they have a lower density and you get that nice rolling boil. And so the definition of the boiling point is the temperature. Boiling point is a temperature, not a pressure. I want you to make sure you understand that. The temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. And at 1 atmosphere, which is 760 millimeters of mercury, we call that the normal boiling point. And we label that T sub B, the B for boiling, T for temperature, and a little circle up here. That circle means 1 atmosphere. This means our standard state. We sometimes call that a TB naught. 0 is a naught. Now, on the diagram up above, you'll see that line drawn in. You'll see 760 millimeters. Oh, stop jumping around on me. That's 760 millimeters. That is a little frustrating. Sorry about that. And that's our 1 atmosphere line. So what happens is, as we come across that 1 atmosphere line, wherever these liquids cross 1 atmosphere, that's the boiling point. And look at where water crosses 1 atmosphere. Water crosses 1 atmosphere, where the standard boiling point of water is 100 degrees Celsius, and that's our boiling point. So we can read the boiling point for any liquid by looking at this diagram and by just reading the temperature at which the vapor pressure curve crosses that 1 atmosphere line. Now, some of you may be thinking a little trickily and saying, hey, wait a minute. What if I lowered the temperature? I lowered the pressure. What if I say go up to Denver that it's a mile above sea level and it has a lower atmospheric pressure? So the lower atmospheric pressure, Denver's atmospheric pressure is somewhere around 600 millimeters of mercury. I believe that's about it. So lowering the atmospheric pressure is going to lower the boiling point because it's going to lower where that line intersects the actual atmospheric pressure. So I said it's going to be where we intersect the actual atmospheric pressure. It doesn't have to be 1 atmosphere if we are not at 1 atmosphere. So if Denver is, say, at 600 millimeters of mercury, come over here. And one of the homework questions is going to ask you to read from that graph, estimate the best you can what the boiling point of water would be in Denver. And this is why we have special cooking directions. If you ever lived at an at a higher elevation in Denver or other higher elevations, you know that you have to follow different cooking directions because the water boils at a lower temperature. And thinking back to yesterday's lesson, where the water stays at the same temperature until it's completely boiled, it's going to stay at 100 degrees C or whatever the temperature is. So if it stays at a lower temperature, food is going to take longer to cook because there's less energy available to you. And it's the energy that cooks the food, not the actual boiling process. And you can understand that if you know that you can lower the pressure enough. If you lower the pressure enough, the water will boil at room temperature. And I'm going to post a video that shows water boiling at room temperature, and a little bit more in that video as well that's going to go along with it's on the back of this. The funny thing is, we think of boiling as a process that needs a lot of heat. You got to put heat in, which is true at room pressure because you have to break those intermolecular forces. But since evaporation is endothermic, so we're going to absorb energy. When you boil water at room temperature by lowering the pressure, and room temperature, let's come up and look at this up here. Room temperature is about 20 degrees. So right there would be the boiling point, would be the pressure that we would need to get to. And that looks like, I'd guess about 10 millimeters of mercury. So if I can get down to 10 millimeters of mercury, I can boil water at room temperature. And what's going to happen, since the process is endothermic, you need to get the energy for breaking the bond somewhere, and you get that from the water itself. And so the temperature actually does go down. The opposite of doing that is by increasing the pressure. If you increase pressure, you're going to increase the boiling point. So if the boiling point, T sub B, goes up, now food is going to cook faster because you have a higher temperature and you have more energy. And we do that in a device called a pressure cooker. All right, so this interface between boiling and liquid, this vapor pressure line, actually is part of a bigger diagram. And if we turn on to the back, we're going to see that diagram, or onto the next page. Those diagrams are called phase diagrams. And a phase diagram is just a map of the conditions of pressure and temperature under which each of the phases of material exist. So I've got water here, water's phase diagram. And first thing I want to do is put in the different phases. So water is a solid in this region, and a liquid in this region, and a gas over here. The lines that you see on here, these lines are called phase boundaries. These phase boundaries separate the two phases, and it's the equilibrium points for the two phases they separate. So here's our 1 atmosphere line. By the way, on the y-axis we have pressure. These are not linear scales. They've been compressed to show the whole phase diagram. And on the x-axis we have temperature. So we're looking at basically increasing temperature as we move to the right at 1 atmosphere. And this is one way you can remember which region is solid, which region is liquid, which region is gas. As we heat up, as we go higher in temperature, we're going to go from solid to liquid. So we're going to melt. going across there, or if we go the other way, we're going to freeze. And 0 degrees is the normal freezing point or melting point. Freezing point and melting point are basically two sides of the same coin. So 0 degrees would be the normal, and let's see, I want to put a label in there for you. That will be the normal freezing point, and we're going to call that TF0, just like we called TB0. Now, as we move to the right, we're going to cross over the liquid vapor interface. That liquid vapor interface, this line is the same as the vapor pressure curve. So we're seeing the same line coming in here. And as we move to the right here, we're going to get boiling. And as we go to the left, we're going to condense. And of course, at 100 degrees, that was the normal boiling point, which we called TB0, TB naught. Okay, so this phase diagram, you can change phases when you either change the temperature, as we're showing you there, or the pressure. So you can change phases by moving up and down, changing pressure as well. So if I go up or down, I can condense or I can evaporate. So changing pressure can make me evaporate as well. I'll evaporate faster. One key feature about the phase diagram for water that makes it different from other phase diagrams, and you'll see a more common one down below, is that the solid liquid line. So here's our solid liquid line here. The solid liquid line goes up and to the left. It has a negative slope. Now, this negative slope has particular implications. As pressure increases, I kind of have this out of order, the particles get closer together and the density increases. So let's draw a line starting at 0 degrees, because that's the easiest place to draw the line. Oh, what's a good color? Let's use orange. So starting at 0 degrees, I'm starting in the gas phase at really, really low pressure. And as I move up, I go through my phase boundaries again. And I go from the gas into the solid into the liquid. Now, this is important because what it means in terms of that negative slope is that the solid is less dense than the liquid, because as you move up that curve, up that line, the density is increasing. So increasing density is shown in the phase diagram by seeing that we go from gas to solid to liquid first. Most materials are going to go the other way, and you'll see that in our next phase diagram. Two more important points on here, and one of these points you'll see in the video that I told you about. So at 0.0098 degrees Celsius and 6 times 10 to the minus 3 atmospheres pressure, we have what's called the triple point. The triple point is a special point. Oh, I didn't fill in this. As the particles get closer together, the density increases, and as I said, the liquid has a higher density than the solid. And again, that's pretty unique for water. Okay, now this triple point. This is the point of temperature and pressure, and most materials have at least one triple point at which all three phases coexist in equilibrium. Now, this is assuming that there's no energy going in or out, no molecules going in or out. So nothing's changing. And in fact, what we're going to have here is boiling ice water. And that's a really cool thing to see. So you'll see that on the video. The other important point, let me change colors. Let's go to the dark orange. Oh, we used dark orange already. That's okay. Oh, that went too high. So the triple point is the point up at the top. Stop moving around. The point up at the top of the liquid vapor interface. This is called, as I say, triple point, the critical point. This is our critical point. Let me rewrite that. Critical point. Now, the critical point, you notice up above the critical point, there is no more real, there's no line, because what happens at the critical point, we can draw a line up above here. And the critical point is really defined by the temperature above which a gas cannot be liquefied at any pressure. In other words, you can't compress this enough. Down at lower temperatures, so down here, you can compress a gas or liquefy a gas by compressing it. Up above the critical point, you can't. And instead of having a regular state of matter, there's really another state of matter here. So everybody thinks that the fourth state of matter is plasma, but it's not. It's a supercritical fluid. And the supercritical fluid is a very special fluid. It's like a very, very dense gas, or like a somewhat less dense liquid. So supercritical fluid extremely dense gas. Oh, I wish it would stop moving. Extremely dense gas, but it has the properties of a liquid. And one of those properties is it can dissolve things in it. And so one of the examples of a supercritical fluid is supercritical water. We can use supercritical water, which is basically safe to use. It has no poisons or anything in it. Old methods of decaffeinated coffee. So we're going to decaffeinate coffee with supercritical water. Old methods of decaffeinating coffee would use harsh chemicals to dissolve the caffeine. Now we can use supercritical water, and when you bring it back down to normal conditions, the water just goes away, and you're left with the clean coffee beans. Finally, down below, we have the critical, phase diagram for carbon dioxide. Now, we see the same sorts of things. We see a triple point here. We see a critical point up here. We see various temperatures. But one thing that's interesting, and we see that we have a positive slope here on the liquid, on the solid liquid interface. So let me just draw that line for you for a moment, the line that comes up. Purple. So just to the right of the triple point, let's come up. And as we come up, you'll see that we go from the gas to the liquid to the solid. And so the solid liquid interface with a positive slope. And so the density goes solid, increases gas to liquid to solid. So solid has the highest density. But there is one interesting thing about carbon dioxide. Notice where the 1 atmosphere line is. The 1 atmosphere is below the triple point. The triple point is higher than atmospheric pressure. So at normal atmospheric pressure, when we increase the temperature, when we put energy in, the interface that we cross over is not the solid liquid interface. We're going from the solid to the vapor interface. And that's why carbon dioxide sublimes. It has to do with weaker intermolecular forces. Carbon dioxide does sublime. In order to get it to a liquid, you can make it into a liquid. But to make it a liquid, we need to get the pressure greater than at 5.11 atmospheres. And so if we can get that pressure up to 5.11 atmospheres or higher, we'll get to the point where we can make liquid carbon dioxide. All right. So this is rather lengthy. Sorry for the length of this, but I wanted to get it all in. Look at phase changes, the phase change of vapor pressure or vapor evaporation and boiling, and the maps, the phase diagrams of the different regions of pressure and temperature at which we find the different phases of a material. So the homework tonight, it's just 2 sides, so nothing to worry about, just a regular 2-sided homework. And I will see you in class next time.